Right. So today's topic is about double integrals over a region which is not necessarily rectangle. Right. So first of all, let me give a definition of this. How do you define? The idea is simple. You just use a rectangle to cover the region, and you set the function to be 0 outside the region. Then you get a function define a whole rectangle. Then you can apply the can value the double integral. Okay, here's the idea. Okay, so you let B be closed, bounded region. Okay, in R2. Okay. And f be a function defined on B. Okay. Now, how do we define the double integral of f? Well, you can use the original definition, partition this but it's easy to it's not easy to add them together. So you can basically draw, look at all those squares which intersect with a region. Then those squares, see the double integral of f dA is going to be still going to be the Riemann sum. Okay, but then you have to be very careful. You have to be very careful about how to count those, because it's not a rectangle. I cannot say I from 1 to n, j from 1 to m. So I just put a sigma there. And this is as long as the delta xi goes to 0, delta yj goes to 0. Okay, so this is a typical rectangle inside a tiny rectangle, and inside this, if we zone out, zone in, this is a point. Okay, and here's the arbitrary point xij star, and this is a delta xi. This is delta yj. Okay. So you only consider those rectangles which either on the boundary or inside the domain. Okay. Then we don't know how many, right? It depends how small the rectangle. As long as this Riemann sums, you got lots of numbers. Okay. Every time we have a partition, and after you choose the points in the rectangle, as long as those numbers approach a fixed number, when the size of small rectangles approach 0 uniformly, then this is denoted by this notation called double integral of f over d, and it's easy to solve to get another formula. Actually, you can take an arbitrary rectangle, cover that region, okay, and it's from A to B, it's from C to D, okay, and this can be shown that it's easy to, this region is we call the R now, okay, yeah, this is the region called R. So it's easy to show that this will be the double integral of f2. Okay, what is f2? F2 must be defined on the whole region, right? So if this is a point is in the D, otherwise we set this to be 0. It's not in the D. Okay, it's in the domain minus outside D. Okay, that means outside D, but inside the region. Okay. Okay, so you set this to be 0, f2 dot to be 0 here, and f2 dot equals f inside. Okay. Then so there's a couple ways to do, but the second definition, they're equivalent. Okay, so it's much easier to understand. You just extend the function. Okay, and then extend the function, then set the function to be 0 outside the region, right, of the domain. Then you get a function defined on a rectangle. Now, this integral is really independent of the rectangle, the choice of the rectangle, because anyway, outside the region, this is going to be 0. So you don't, even you change another rectangle to cover that region, you still get the same limit, okay, assuming this exists. Okay? Now, question is whether this is still whether we can still use a forbidden theorem, because f2 dot is not a continuous function. Note that, right? So whether we note that f2 dot is not continuous on R, although f is continuous on D. Okay, but so the question is, yes, the domain right now is nice, it's rectangle, but f2 that is not a continuous function. Can we still use the forbidden theorem? The answer is yes. Okay, but you have to be careful about this. Here's a theorem. Okay, the forbidden theorem is huge, can be used, still holds for this type of function if D is a closed bounded domain and with a very nice boundary. Okay, the boundary cannot be very terrible. It's a closed bounded domain with a continuous boundary. Okay, with a nice boundary. I'm not going to talk too much. Most of the example we don't worry about it. With a nice boundary, a good boundary. In mathematics, it's like it consists of several lines and several curves, smooth curves, and f is continuous. Right? Then this double integral f dA equals this double integral of f2 dot dA, and this can be calculated using the iterated integrals. CD, f2 dot, xy, dy, and dx. This is also equal to CD here, AB, f2 dot, xy, dx, and dy. Okay. So you can still evaluate this double integral of f2 dot over the rectangle region and using iterated integral, because that's the only way we can evaluate integral. Otherwise, it's hard to do that. You have to find the limit of Riemann sums. That's really, in general, it's almost impossible. Okay. So my first example I want to discuss is this first. Right. I evaluate this double integral and x plus 2y dA. Right. So this is a function, linear function, but what is d? How can I describe d? D is is a region bounded by y equals 2x squared and the line y equals 1. Okay. Yeah, let me simplify a little bit. I don't put the 2 here. Right. All right, so first of all, you have to draw the region, right? So this is a parabola open upward, and this is a line. Okay, so that is my region. Yeah, this is a region. Yeah, this is a D, right? So we want to integrate this function over that D. Okay, what we're going to do is you use a rectangle to cover that. Okay, this is our rectangle. Okay, so the rectangle, let's write down the rectangle we cover it. It's going to be x is from negative to positive, y is from 0 to 1. Okay, so this covers the D. Okay. So our function right now is x plus 2y. That's on D. Okay. So this f2 dot is going to be x plus y, right? If inside the D, right? How do you say inside D? Inside D means actually if x y is in D. Now how to describe this point in D? So it's above so in other words, y greater than x squared. As long as satisfies this condition. Okay, then otherwise it's 0 if x, y is outside D. Okay. All right. So now let's evaluate this double integral. The double integral f dA is going to be this double integral. Okay. Then we write down all the two iterated integral. We decide which one is better. Okay. So the first one is the integral x is outside, y is inside. Okay. Y is inside, so from 0 to I, and here's f2. I cannot replace f2 yet. Okay, so this is dy dx. Okay, let's look at this. Okay, y2. I think when y is when it's 0. Okay, fix x, right? If y is greater than equal to x squared. You look at this x, okay, look at x, you draw the line here, okay? For y between those two numbers, it is going to be x plus 2y. So I think the smallest value should be x squared, the largest value is y. And then I can replace it by x plus 2y, okay? Why? Because this is going to be 0 if y is less than x squared. Okay, right? When you say x, y outside D means if y is less than x squared. Okay, below the parabola. Okay, so it's less than, so that's why the integral with respect to y variable, when y is small, it's already 0, so we can ignore it. Okay, so this is y integral. And we can finish that first. We can compare which one is best. Sometimes you have to decide x first or y first. Okay, that makes some difference when we evaluate integral. All right. Now, x plus 2y, the entire derivative with respect to y will be xy plus y squared. Okay. Then you plug them. You have plug 1 for y as x plus 1 squared minus x times x squared plus x squared and squared. Okay, so you get a polynomial. Every place with y replaced by x squared. Okay, let's simplify a little bit. Okay, I have a 1, I have an x, I have minus x squared, x cubed. Okay, minus x to the fourth power. So this is a polynomial, not too bad. Okay, so you get, and when you integrate, you know, the power function of other power, the integral will be 0, but you can keep it. This is x, this is half of x squared, this is going to be 1/4 of x to the fourth power, this is 1/5 x cubed. Okay, evaluate the two endpoints. This gave me 2, this gave me 0, this gave me 0. Okay, and here is also giving me 2 because 1/5 minus -1 is 2. Okay, you can do that. Okay, so the answer is 1/2/5, 8/5. So that is the answer. Okay, yeah, you can do this part. So our next, what I'm going to do next is I'm trying to use a different, order of the iterative integral. So this time, this double integral is going to be the y variable. This is because the r is here, right? So this is -1 to 1 and 2. So I put the y outside. It's from 0 to 1. Then x is from -1 to +1. And this is still f2 now, okay? dx. All right, so now we focus on the integral inside. We focus on the integral inside. And for the fixed y, x going from here to here, right? From this whole line. But you notice that when x is outside this line segment, I'm going to color it. When x is, when x is outside this line segment, f2 that is given 0. So they can be ignored, the integral, right? All I need is for the fixed y, what does this point x? Okay. Can we find it? I think so. For the fixed y, because this is parabola. So parabola is y equals x squared. But the x is going to be plus or minus square y. Okay. So this will be positive square y, will be negative square y. So now I can replace this by negative square y, positive square y, then f2 dot xy. Since over that interval of x, f2 dot is, the points is along this line, right, with the y fixed. So f2 dot can be equal to f. That which is going to be x plus xy plus y squared. So that is dx, okay? Then dy. All right, so now we find the antiderivative of this function with respect to x. I only have one x here, so it'll be half of x squared y plus y squared x, okay? And then evaluate the two endpoints. I think the first term will be gone because x squared is x squared part of a square root of y is going to be x is going to be negative square y squared. So that cancels out. What you have here is twice of square y. Okay, because this is this is x here, right? So that means square y minus negative square y is going to be y square y. Okay. So now you will get 2y, 2 plus 1/2. 2 plus 1/2 is 5/2, right? So you get totally different function. Now, to find the antiderivative, you will get 5/2 plus 1. Okay, 5/2 plus 1. and this is y to the 5 over 2 plus 1. Did I make mistakes in computation? I'm going to go back. Y to 8 over 5. All right, let's double check. We should get the same answer. All right, I'm going to double check. Okay, let's finish this first. All right, it's from 0 to 1. Right, so you get 2. It's 5. That's inverse. Okay, 7 over 2. Right, 1. So you will get 4 over 7. Now we have to find our mistakes because the theorem says that they're guaranteed. They should be equal. Okay, doesn't matter which way you do the first. So let's go through the first one. Okay. All right, so this is an iterative integral, right? And x plus 2y. Did I get use x plus 2y? Here. Yeah. Yes, that's my mistakes. X plus 2y. Let's go back to the function. That's why I made a mistake. Copied the wrong. Okay. I copied the wrong. I copied the derivative x plus 2y. Right. Then I should have a x plus 2y. Right. Yeah. Let's finish it. So the function, original function is x plus 2y. That's the original function. Yeah. Then this will be half of x plus 2xy. Okay. And so I will have so I have a 2y here. X is going to give it to me. Okay. So yeah, let me erase this part. Okay. Yeah, I did not copy the original function. That's right. So I have a 4 here. This will be 3 over 2. Okay. So the entire derivative is 3 over 2 plus 1. Okay. And the y to the 3 over 2 plus 1 and very thin. Okay. So we will get, after we simplify it, so it's 4 over 5 over 2. So that is going to be 8 over 5. So we get the exact same answer. So it doesn't matter, right? Which way we do. But just careful, when you do the computation. Okay. So this is a good example, and you have 2 different ways to do it, and I don't see which one is better. I don't see which one is better. Okay. You can compare, right? Yeah, be careful when, yeah, let's take a look at another one. Okay, another example, the domain would be a little bit difficult, okay? So sometimes you don't have a choice to, there are 3 different ways to find the iterative integrals. 2 different iterative integrals, but one of them is very difficult to handle. And in that case, you are forced to use one of the iterative integrals. So that's really make it very simple. Okay, so you have to make a wise choice at the very beginning. So this is double integral. Okay, and the D is the region, right, bounded by the line y equals x minus square and y square equals 2x plus 6. So I wanted to try to sketch the domain first. Okay, I wanted to sketch the domain first. You should be able to do that. Okay, sketch the domain. I give you a minute to sketch the domain and you solve the problem. Okay. Right? How do you sketch the graph, right? It's a when the parabola, okay? When is the parabola and when is the line? Okay, the line is going through this. Okay, parabola is open to the right. You know, you can write it in another way. Okay. Right, so this parabola, how do you draw the parabola, right? So x equals half of y squared minus 6. So it's half of y squared minus 3. So the vertex should be here, right? And the parabola is like that. Wow, so that is a region. Don't make mistakes on that. So you have to find the intersection point. Okay, how do you find it? Well, intersection points, you can find it in a couple ways. You can replace x by y, so y plus 1 plus 6. So you get 2y plus 2 plus 8. So y squared minus 2y minus 8 equals 0. Okay. So what is the y value here? Okay. I think it's a y minus 4, y plus 2 equals 0, so y equals -2, y equals 4. So -2 is here. And this is a 4, okay? So when y equals 4, x is going to be 5. When y equals -2, x is -1. So we got 2 parts. Right, then you have to decide, you have to find a rectangle to cover it, right? So let's use the red pen to cover it. I don't need a very big one, but at least I need this size. All right, so this is a rectangle. Now, so here's the F tilde is going to be F, right, over here. But here F tilde is 0. F tilde is 0. F tilde equals 0. Yeah, so this is a domain we have here. So we were told that this double integral of d, that's a d, of f is going to be the, this is r, right? It's double integral over this rectangle region. Then you have 2 different ways to set up the iterated integrals, right? And I think here's from -3 to 5. Here's 5. And this would be -2, the top is 4. So I is going to be -3, 5, and then -2 and 4, right? Make sure this is right here. All right. So we have 2 different integral, iterated integral, and which one we have to choose? This is x is outside and y is inside. Okay, another one. Oops. Okay. Another one will be x is outside, y is outside, x is inside. And how do we solve the how do we solve this problem now? Which one is better? Okay, if I choose, okay, so let me draw the picture here for either one. Okay, where's my picture? Yeah, this is it's going to be like that. Right. So if I choose the first one, what I have to do? I fix an arbitrary point x, right? And then I draw the line, vertical line. Okay, then this is a, you see, Then for the fixed x, I have to figure out the lower bounds for the y variable, upper bound for the y variable, right? So the question is, what are those 2 points? The top one is easy to find out, but the bottom one depends on the location of the x. Sometimes this is 2 points on the boundary of the on the parabola. Sometimes the lower point is on the straight line. So that's a really bad idea. It's harder to describe f tilde, the f tilde. Okay, so I don't think we should use the vertical line for the first iterative integral. Okay, that's the trouble. Right. All right. Now, so the first integral, it's harder to simplify this part. Okay. So my question is, yeah, who can do that, right? Yeah, you can simplify for fixed x. But then it depends on the location of x. It depends on the location of x. Yeah. And then, f tilde is defined along this, defined for the fixed x, f tilde is defined along this vertical line, okay? But then somewhere it's 0. Only on this line segment, vertical line segment, it's not 0. Okay, so it's not easy to do that. Now I switch to the second iterative integral. The second iterative integral, I still draw the picture here, and I'm going. Okay. For the second iterative integral, and the lowest point is going to be -2, right? And the top one is -4. So let me draw it. Okay. So this time I'm going to use fix the y, use a horizontal line. Okay. Use a horizontal line. And this is a part. It's inside the domain. All side f tilde is 0. So I needed to figure out for the fixed y, I needed to figure out what is this, right? And for the fixed y, what is x here? What is x here? Like we can solve it, right? The corresponding x, this is on the line. So the line equation for the line is going to be, y equals x minus 1. So x equals y plus 1, okay? So for x greater than that number, f tilde is 0. And how about this one? This one, I needed to find x. So actually is going to be, it's on the parabola. So x is going to be half of a y squared minus 6. Okay? So for x less than that number, it is going to be f tilde is going to 0. So that's why you can just let this be y plus 1, and here is equal to f of x. Okay. Yes, because f tilde will be 0 over this interval and over that interval. Okay. Now we are done, right? Okay, let's go back. So what is f of x? F of x is just x. Okay, so it's dx. So you can evaluate this. Okay. So now the double integral df is just x, right? Yeah, f. Let's use that. Our f is x. This is going to be the integral for the y value from negative. Okay, and this is going to be half of y squared minus 6, half plus 1. and this become f. Yeah, it doesn't matter which function you use. Now in our case, the function is that's 3. Okay, minus 3. After minus 3. Yeah. Okay. Okay. So y plus 1, here's x and the dx. Okay, then you evaluate this integral. The antiderivative of x with respect to x is going to be half of x squared. So you will get half of x squared and evaluate at those two endpoints. Okay, then you will get right. We have to simplify. Okay, I'm going to take 1/2 out. Okay, this is y squared plus 2y plus 1, and this will be 1/4 of y to the 4th power. Here's 3y squared plus 9. More twice of this. Okay. Hold on, yes. So then you simplify it. It's a polynomial anyway, right? So you get negative 1/4 of y to the 4th power, and we have minus actually 4y squared, and you have a plus 2y. 1 minus 9 is -8. Okay. Then you have to use the antiderivative. Okay. So you can evaluate this integral. Okay. So everybody know how to do this, but it's computationally really complicated. So antiderivative for y to the 4th, that is going to be here. Okay, and here's 4 over 3 y cubed, and here's 2 over 2 just y squared minus 8y, and evaluate the two endpoints. Okay. So I'm not going to finish the last step computation, just the numbers, the fractions. These should be very careful when you simplify. All right. So only one iterative integral works. The other one, it must be a piecewise defined function. So it's not recommended. Right. All right. Let's continue to do some other exercise. We have the double integral of y and dA. Right. Let me describe the d. How to describe the d? Right. So the d is not given by the equation. So this is a 1. Here's a 2. Right. So this is my d. There's a triangle. That's it. So this x-axis to this y-axis, that's it. I wanted to try to set up a 2 iterative integral. And yeah, if you can. Okay. So this is the f here, f of x over the d, right? It's going to be y. But the f2 dot, you use this rectangle, okay? This is R, right? So I is going to be from 1 to 2, from 0 to 1. Okay? So you extend the f2 dot, here's the f2 dot equals f, here's f2 dot equals 0. Okay, so this is a double integral. Is going to be the integral of f2 dot here, okay? Now you have to change it to the iterated integral. And both works, I guess. And you need to write down. Yeah, can you do that? Yeah, give me two iterated integrals for this double integral. All right. I hope you make some progress. And so first thing you have to do is, yeah, let's see. So you write down two iterated integral, okay? If you put the x all sides from 0, right? So that would be dx. Then the y is from 0 to 1. f2 dot xy dy. Another one will be from 0 to 1 and from 0 to 2, f2 dot xy dx and the dy. So you have to figure out those two. Okay? So let's look at this pic. Let's look at this one. Okay, and here's a picture again. So this is a 2, that's a 1. Okay, now can you find the relationship between x and y? I just want to write down. Okay, it's going to be x is going to be negative 2y plus 2. Okay, or y equals half of x, or y equals negative 1/2 x minus 2, either way. So that is the equation for the line. Okay, slope is negative 1/2. Okay, and why we need that? Because I know I do need it. Okay, for the fixed x, I want to see for what the y value is still inside the domain. Okay, for the fixed x, the y is going to be negative 1/2 of x. So that means f2 dot xy, okay, is going to be our original function is y, if y is smaller than, if y is, for points along this line segment. Otherwise, it's going to be 0, right? So, so I'm not going to define this. This is f2 that is a piecewise defined function. So you can just say for fixed x, if y is from 0 to negative 1/2 of x minus 2, and f2 that is just equal to f, which is y. Right? Yes. Okay. But for the second one, this is the time we're going to evaluate the integral for with the y fixed. The y fixed is we are on this horizontal line. On this horizontal line, for which x value this line segment is still inside the domain, for x from 0 to, here's y is fixed, so to negative y plus 2, okay? Because this is x is going to be negative. For fixed y, x is going to be negative 2y plus 2. So this is still y dx. Okay. Personally, I think the second one is slightly better. Because when you find antiderivative, I do not immediately get squares. So I'm going to use, but use both of them still correct, okay? So the iterative integral, let's use the first one, and that is going to be from 0, negative 2y plus 2, and this is y dx and dy, okay? And the antiderivative of y with respect to x is just yx. Okay, and dy. So when you plug this, I get y negative 2y plus 2 dy. Okay, and finally, I multiply this out. I get the antiderivative negative 2 over 3 y cubed plus y squared evaluated to end point. So I get negative 2 over 3 plus 1, so that's 1/3. Okay, 1/3 is our answer. Now, if you really still want to use the other one, I think I still get the same answer. Otherwise, something's wrong, just like what I did last time, right? I have to go back carefully check it. Then I find, oh, no computation mistakes. I just copy the function one. All right. So we use the first version of the iterative integral, right? So which is from integral from 0 to 2, and from 0 to 1, f2 dot xy dy and dx, right? All right, so this integral, here x is fixed, right? X is fixed, so y is between 0 and negative half of x minus 2. From 0, negative half of x minus 2, okay? And the function here is y, okay? So dy and dx. Okay. Then the antiderivative of y with respect to y is going to be complicated. It's half of y squared. Right? Evaluate this to end point. You have to square it. It's fine, square it. And this will be 1/2, negative 1/2, right? X minus 2 squared dx. Okay. So we will get, I think 1/8. I'm going to put it outside. And x squared minus 4x plus 2 plus 4, right? And then evaluate this integral. Okay. Antiderivative. Okay. All I need is just plug 2 squared 2 cube minus 2 cube plus 4 times 2. I think that's canceled. That canceled out. That was just only 1/3. So, well, great. We get the same answer, right? Yeah. So for this particular problem, I still cannot tell the bigger difference. Okay. I cannot tell the bigger difference. Which way is better? Right. Which way is better? Now, sometimes you have to solve an inverse problem. And you are given the iterative integral. You have to figure out my original domain, right? So here's a question. I think it's from 48, okay? Okay, this is a very challenging problem. Okay, sketch the region of integration and change the order of integration. Okay. So we have because the function is not given either. Okay. So what I have to do? Yeah, I want to go through the middleman. Okay, I want to go through this double integral d of f of x and dA. Then I switch it. I switch it. Then here's the f of x, dy, then dx. But I don't know the interval yet, right? So I have to find out the d, the region of the integration. Then you can go the other side. Okay. So what does that mean? Okay. So let's go to here. So this is actually is going to be -2 and the +2, right? And the kind of interval, from 0 to some number, okay? And this is the f2 dot. Okay. So this should be a number, not this. Okay. Then the outside this, yeah. So here's x, y. So y variable is between -2 and the +2, okay? So for any y variable, x, y, okay, my function x is from here all the way to here, stop. Because all sides it's going to be 0. So for this x, right, the upper bound for the x, the lower bound for the upper bound for the x is going to be 4 minus y squared, okay? So actually x is between those two numbers, right? Then you have the integral, you see, with respect to x from 0 to square 4 minus y. Okay. Right? So x for fixed y, and my x changed from 0 to this. So you can find the relationship of the point of this point. The relationship of this point is going to be x equals square root of 4 minus y squared. Okay? And then when you square it, you can also get x squared equals 4 minus y squared, or x squared plus y squared equals 4. So this is just a portion of the circle. Okay. So we determine the domain. Okay, we determine the domain. That's the reverse procedure of this. Yeah, we determine the domain. Okay, so this is our D. So the top one, actually, we can put the 4 here. Okay, we can put not 4, it's 2. Yeah. So we are using a rectangle. Okay. But anyway, so we get the domain. Okay, these semi-disk, okay, on the right-hand side. How did I get there? I just want to see where x for, for a fixed y in the interval from -2 and 2, my x is between 0 and 4 minus y squared, okay? Right? Just based on the above iterative integral. X, is between this. So the largest one, then you look at the equation. Okay, this is the the boundary. Okay, so then you can get x squared plus y squared equals 4, but x should be always positive. This is semi-circle. All right. So now once you get the domain, then you can change the order, right? So let me draw the picture again. This is semicircle. Okay. So this time, here's 2, here's -2. So integral from 0 to 2, and x should be outside, and then inside will be the integral with respect to y variable. So that means I'm going to fix x, and I look at my rectangle still here, right? Then look at all the points here. So this is y, here's x and y, right? So for fixed for a fixed x in the interval from 0 to 2, what does the y variable allow, right? The y variable allowed so that the point is still inside the domain, so y should be greater than, less than, equal to. You solve for, look at the equation, okay? So I think the upper one will be 4 minus x squared, the lower one is -4 minus x squared. Okay? It's a between, between those 2 points. Then you put it back. Then the integral from here, okay? So we're there. See, it's not easy to do this problem. Okay, you interact. We do. Let's try another one. Okay. Let's try another one. Okay, we have an integral from 0 to 1, from x squared to 1, and this time my function is also given. Okay. Now, why we have to iterate? Why we have to change the order? Try, because when you look at this iterative integral, if you really want to evaluate this integral with respect to y, I don't think it's easy. We can try, but it's not easy. Maybe you cannot, because there's no way you can evaluate this integral, basically. So what I try to do is, this is my f, right? What I'm trying to do is, I want to figure out what is the domain of this integral, okay? Once I got this, I can change the order. Then maybe there's a chance for me to evaluate this integral. So I don't know the interval yet. Okay. So let's take a look at this. Let's figure out the d first. Okay. If after change the order of the integral, maybe we are able to evaluate. Okay. So what is d? So I'm going to look at the iterated integral, right? For a fixed x in the interval from 0 to 1, my y variable is between x squared and 1, right? Right? From above. So So now it's clear. How does the picture look like for x, fixed x? The y variable is between 1 and the y variable between x squared and the 1. Y equals x squared is a parabola, right? Between 1 and x is somewhere here. This is a whole, this is a, yeah, we describe all the points around this, okay? So when x runs from 0 to 1, yeah, this is y equals x squared. The lower bound for y is x squared, the upper bound for y. So you end up with this region. Okay, that's good. So that's my d. Now once we get d, then I can do the for others. Okay, so then I can say for fixed y is also in the interval from 0 to 1. And what is x? What is x? Okay. What is the x variable? So that the point is still inside the domain. Okay. So the x variable is clearly the lower bound is 0, right? The upper bound depends. If we solve for x, that should be square y. Okay. So then I can go back to the integral, right? The y variable is from 0 to 1. The x variable from 0 to square y. Okay. Then I still have the function f here. So the function f is a square y sine y, okay? But once you make such change, and the integral becomes very simple, okay? The integral, let me copy this integral. This is x, right? And dy is outside, yeah. So square y sine y is nothing to do with x, so the antiderivative is just this times square y. Then you have an integral y and sine y and dy, and that is going to be simple. What? And why? We use integration by parts. Okay, so let's find the antiderivative of this. It's going to be y. This is going to be d negative cosine y. Okay. Then you will get cosine y and minus as a plus, and that to be cosine y dy. Okay, so you can quickly get this antiderivative. You can double check that. Okay, so when you differentiate this, you get cosine y. Yes, that. So the antiderivative is negative y sine y plus sine y from 0 to 1. And my answer is negative sine 1 plus sine 1, right? Oh, cosine. Cosine. All right, it's just sine 1 minus cosine 1. That is the answer. But if you do not change the order of the iterative integral, then it's very difficult to evaluate. Okay, so look at this original integral, right? How do you evaluate? Use the integration of parts. I cannot get rid of the square root of y. I cannot get rid of square root of y. Yeah, the question is who can evaluate this integral, right? When you use the integration of parts, you're not getting rid of the square root of y. There's no way you can simplify. All right, so my next question, yeah, let's try it again. So it's from 0 to 1, from 0 to 1, okay? And this is a integral from x squared to the x. And this is just a function, okay? And that's y and the dx. Okay? I want to exchange the order of the integral. Now, some students just switch it. The result, if I understand, is iterative integral. You know, all sides you cannot put x squared x. Okay, this is not going to be x squared x. Then that is totally, you don't get any partial credits if you just simply do like that. Okay, so they're not equal. Okay, you needed to understand what is the iterative integral. So first thing you have to do is to determine the domain of that domain of the, you have to determine the region described by this iterative integral. Okay, so how do I do that? You see, look at this, the x is all sides, so I'm going to fix the x, okay, and fix x. And what is y value? Y value is between x squared and x, right? For this integral, right? For the fixed x, you work on the integral inside, so x is fixed. The y is between x squared and x. So now it's clearly you can get the picture. X is between 0 and 1. Y is between actually this is going to be the region. Okay, y is between those 2 points. Okay. So this is y equals x. This is y equals x squared. So clearly this inequality describes the region, right? Yeah, that's the region. And that's my D. Okay, so for the same D, yeah, this is x, right? And the y value, and the arbitrary point here, x and y is between x squared and x. But for the same picture, I can describe it using fix the y variable. Then I draw a horizontal line. And the arbitrary point here, x and y. For the x, I have an upper bound and I have a lower bound for the fixed y, right? So for if you fix the y variable in the interval from 0 to 1, oops. I saw it disappear. All right, so where's my picture? So let it go. Disconnect. Okay, I'm going to redraw the picture again. Okay, so fix the y variable in the interval. Does not allow me to continue my lecture. Okay, so it sounds like I'm not able to use my computer right now. Okay. I'm not sure I can finish this example. Right. So what I'm going to do is, for the fixed y variable, I try to determine the x value. Okay, here's an arbitrary point. Okay. So you have to tell me what is the lower bound for the x, what is the lower bound for the y variable. So x is greater than or equal to y. Okay, the y variable, I think x You see, y equals x squared. So x is going to be square y. So that's why the upper bound for the fixed y, the upper bound for the x is a square y. Okay. So that's it. And then you can write down the iterative integral. The integral is from 0 to y. Y is from 0 to 1. Okay, and the x is from y to square y, and here's f of x dx. Okay. All right, so that's all we discussed here today. So if you're able to understand those three problems I discussed at the end of the class, then you understand iterative integral pretty well. Okay. So sometimes you have to, you're given the iterative integral, you have to figure out the domain of the double integral, then you switch the order of the iterative integral. Then you can evaluate the integral much better. Okay. I stop here. Okay. Now we are going to have a full review class next week. Don't miss it. And then we have a test, midterm test.